Welcome back everyone to the graphene unit. Until now you have learned what topology means for a single sheet of graphene. Now let's consider two sheets of graphene on top of each other with a slight angle misalignment between the two. This is a completely different quantum system, and it's a one that is highly tunable, and it allows to see very exotic correlated physics. It has gathered a lot of attention, and every day there's new theories and new experiments coming up to show more properties of this system. We don't know everything about this system, but one thing that we do know is that its band structure and topology are critical to allow for such correlated physics. And this is what we're going to explore in this lecture. So let us review what happens to a single layer of graphene. We have singularities in the wave functions at k and k prime points, which correspond to the Dirac points in this system that carry a winding number and a chirality. This is well defined because of the symmetries of the problem. Particularly, graphene is time reversal symmetric. It has a spinless time reversal symmetry because it doesn't really have spin-orbit coupling. And it has a very good particle hole symmetry that relates the spectrum from positive to negative energies. This implies that there's a proximate chiral symmetry in the system and puts any path that surrounds a Dirac point in the class A3, which allows for a well-defined winding number. So any general two-band Hamiltonian can be written in terms of Pauli matrices. So if we just write the Hamiltonian as a D vector, where D1 is proportional to sigma x, D2 sigma 2, sigma y, and D3 sigma z. If we take sigma z to be the representation of the sublattice, meaning the eigenvalues of sigma z is the position A and B, the sublattice A and B of the graphene unit cell, then we know that this symmetry tells you that these two sides are the same, and you cannot put any disbalance between the two. There's no terms in the Hamiltonian that are going to be proportional to sigma z. It means that the Hamiltonian will anti-commute with sigma z, and this D vector will be an in-plane vector that allows for these vortices. Now we can ask, is there any exact symmetry that accomplishes the same thing? And for that, let's look at the low energy theory of the Dirac points. This is how you write it. We need to be very careful to have a basis which is compatible between the two Dirac points. The Hamiltonian is located at the k and the k prime values, and the sign here determines what is the handedness or the chirality of the Dirac points. So now, if we allow for symmetries which are not internal symmetries, which are spatial symmetries, we can see that there's an additional symmetry that would accomplish the same thing of protecting this Dirac point. And that is a combination of spatial inversion C2 and time reversal symmetry. So let's see this. If I take spatial inversion, I exchange the sign of momentum. So I interchange the two Dirac points. Now, time reversal symmetry also exchanges this sign of momentum. So I take this Dirac point to this side. So C2T, the combination, will act locally on this Dirac point. So by looking at this specific Hamiltonian and how C2, the spatial inversion, acts in momentum, we can see that the representation of this operator is sigma xk. And the terms that commute with this operator are those to linear order which are in the screen. Therefore, the same operator accomplishes to take away any term corresponding to sigma z. Now, one of the most important and powerful things about two-dimensional materials is that they give us an immense playground of tuning their physics and their electronic properties by heterostructuring and combining them together, by combining their unique properties and also the properties of their couplings. So now one fascinating way that we can tune the electronic properties of materials is by slightly misaligning the layers. And this will mean that we'll create additional length scales in the problem and additional patterns which are called Moiré interference patterns. And we can see this in action exactly by looking at a 3D printed sheet of an hexagonal lattice and another one which have a small lattice spacing. But as we put them together on top of each other and we slightly misalign them, we can clearly see that there's a superstructure being created, a much larger lattice with a much larger lattice constant that gets larger and larger as the misalignment gets smaller and smaller. If I slightly twist, you will see this pattern showing up. The larger the twist, the smaller the lattice is created. In the combined system, you can see this superlattice emerging, where now the new unit cell, the Moiré unit cell, has lattice vectors on the tens of nanometer size. And there's different regions in the unit cell that you can identify. Regions where the hexagons from the top layer and the bottom layer are exactly on top of each other. These are the AA regions, we call. And there's regions where the two layers are Bernal stacked. This means that the carbon atom of the top layer is falling right in the middle of the hexagon of the bottom layer and vice versa. And these are these regions. This superstructure is going to be actually reflected as well in the momentum space, in the reciprocal lattice vectors. Here we are seeing the Brillouin zone of graphene with two Dirac points of opposite chirality in the K and the K prime values. These three different and equivalent K points in the Brillouin zone are related by the reciprocal lattice vectors G1T and G2T, where T here stands for the top layer. The bottom layer is going to be to have a Brillouin zone related to the top layer by slightly rotating one with respect to the other. This means that around the same momentum region, we will have two Dirac points of the same chirality slightly shifted by these vectors Q1, Q2, and Q3, which have a magnitude that is proportional to the theta angle. If we zoom into this area, the large periodicity allows for scattering between states related by the reciprocal lattice vectors either on the top or on the bottom layer. So we can redefine the Brillouin zone to the so-called mini Brillouin zone around one of the K valleys, where now looks remarkably close to the Brillouin zone of graphene, but it's related with the reciprocal lattice vectors given by the difference between the reciprocal lattice vectors of the top and the bottom layers. In particular, this can be extremely small if the angle is small enough. And notably, we can also decouple this region of momentum space to the other original K valley of graphene. And that means that we can treat the original K values as an internal conserved degree of freedom. Now we can compare the magnitude of Gm, which is going to be inversely proportional with the Moiré length scale, and we can find that the Moiré length is going to be proportional by the original lattice vector A over theta up to a geometric factor of square root of 3. So from these considerations, we see that the low energy of twisted bilayer graphene is quite similar to the low energy of original graphene, however with a very, very important difference. The Dirac points now have all of the same chirality, and this means that explicitly we have broken time reversal symmetry. However, because it is local in momentum, C2T remains, and that is what is going to protect the vorticity of the Dirac points in this Brillouin zone. Until this point, we have not actually considered any coupling between the top and the bottom layer. And we know that most of the fascinating physics in this system will actually come by looking at this coupling. So in this case, we now need to understand what are the energy scales at play in this problem. First of all, because of the original velocity of the Dirac fermions of graphene, we can construct an energy scale that relates to the momentum space separation between the two Dirac points of the same chirality in the Brillouin zone. This is h bar VF k theta, where k theta is the magnitude of the little q vectors. Additionally, coupling between the two bands will actually mean that the states, the two Dirac points, will couple and will split in energy. That means that there will be a gap opening that has to do with how much tunneling exists between the two layers. One of the energy scales is related to tunneling between different Moiré unit cells within the same layer. The second energy scale is tunneling between the top and the bottom layers. And we can imagine that there is a resonance condition that may appear due to destructive interference, particularly when these two energy scales are comparable. And this is exactly what happens here, and you can already see by hinting on this picture. As this energy scale becomes larger and larger and comparable to the Moiré energy scale, these bands are going to flatten out and the electrons can actually completely freeze. And this is a very interesting phenomena that will appear because of this twist. This was first proposed by Bistritzer and MacDonald in this paper in 2010, where they denoted that these particular angles where electrons completely freeze, the effective velocity of the Dirac fermions goes completely to zero. Those are the magic angles. And we can see here a few different angles, a series of angles where the velocity, the effective velocity, actually completely vanishes. And we can see that this will happen initially when the ratio between these 2 degrees of freedom, which is a dimensional parameter called alpha, is around 1. So how do we go about actually calculating the band structure of the system and the effective velocity of the Dirac points? We need to write an Hamiltonian for this system, and the way that we can do that is by constructing a lattice in momentum space related to the folding of the Dirac points of the top and the bottom layer. At each of these sites, the Hamiltonian will be given by your Dirac Hamiltonian that you have seen before, hk, and here it will be hk plus q, and so forth. But now, because it is possible to scatter between these different points in the momentum space, we must introduce some momentum-dependent hopping matrices that depend on the actual orientation of this hopping in momentum space. It's like a momentum space hopping Hamiltonian. Explicitly, we write the T-coupling matrices in this form, where it allows for hopping between momenta separated by Q1, Q2, and Q3, where T's have the matrix structure of in the sublattice space in the following way, which preserves C3 symmetry, and we see that there's 2 main terms, one that it's diagonal in sigma space, and this term is relevant for those regions of the twisted bilayer graphene where the graphene layers are perfectly stacked on top of each other, so the AA regions, and the AB regions where there's a Bernal stacking of the top and the bottom layers. So now it's important to note that graphene prefers to be Bernal stacked than exactly on top of each other. So what will happen naturally is that the AA regions will shrink a little bit, the AB regions are going to get a little bit larger, and the top and the bottom layers are going to be a bit closer within the A and B regions. So it's naturally to expect that WAB is actually going to be larger than WAA in the real system. However, in the original Hamiltonian introduced by Bistritzer and MacDonald, they consider these 2 energies to be exactly the same. And we can compute this band structure by diagonalizing this Hamiltonian, and here we can see it close to the magic angle. We find that the Dirac points here that exist at the K points, they have a very, very, very small Dirac velocity. And this is labeled by alpha equals 0.575, which is the dimensionless ratio that I've talked about before. Now, if we are going to change a little bit of the ratio between the AB tunneling and the AA tunneling, then we will see that there's a gap that forms and separates these flat bands, the low Dirac velocity, to the dispersive bands. And this is much more in line with what we see in experiments with the mounting experimental evidence that is being collected within this system. So let us note a few aspects of this topology of twisted bilayer graphene by comparing it with the single layer graphene. In single layer graphene, we have two Dirac points of opposite chirality, and the way to gap them is by breaking the C2T symmetry. There's two ways of doing that. I can break time reversal symmetry, or I can break C2 symmetry. So if I break time reversal symmetry, this means that I'm going to put a mass term of opposite sign in both valleys. When we have a gapped Dirac Hamiltonian, this will contribute a Chern number of plus or minus 1/2. And if we do with opposite masses, then we will have a total Chern number in the system. And this is precisely the realization of a Chern band introduced by Haldane in the graphene. On the other hand, if we break inversion symmetry, and this can be accomplished, for example, by aligning graphene with HBN that has a boron and a nitride in different sublattices, then the mass term that we're going to accomplish in both K valleys, it's going to be of the same sign. This means that there's a total zero Chern number and the system is completely trivial. But now we have something completely different. The original Dirac Hamiltonians we started with, they have the same chirality in both valleys. That means that we can break inversion symmetry, open a mass gap with the same sign, and necessarily the total Chern number is going to be non-trivial. So we would expect that just by breaking inversion symmetry, simply by aligning with HBN, we would find a Chern band in our material, and we would find anomalous quantum Hall effect.